In September of 2017, something entered our solar system from outside it. It had traveled for an unknown distance through interstellar space before arriving. It passed closer to the Sun than Mercury. Then it turned and headed back out into the dark, moving at roughly 70,000 miles per hour. None of that is particularly strange. Small objects pass through the solar system regularly. What was strange was the shape. Scientists who analyzed the trajectory estimated it was unlike anything in our solar system. Extremely elongated, with proportions so unusual that no natural object previously observed had ever matched them. And then there was the acceleration. As this object moved away from the Sun, it sped up. Not because of gravity. Gravity would have slowed it as it moved further away. It accelerated beyond what gravity alone could explain. When astronomers searched for the most obvious cause, outgassing, jets of sublimating material pushing it like a natural thruster, they found nothing. No gas trail, no visible cloud of debris, no coma, no tail. Just an object moving faster than it should be, with no visible reason why. When the paper came, it was not from a fringe researcher. It came from the chairman of Harvard University's astronomy department. And it proposed in careful, peer-reviewed language that the most consistent explanation for what was observed was that this object was not natural at all. We have never been able to rule that out. This is the story of Oumuamua, the first object ever confirmed to have entered our solar system from interstellar space. And what it did while it was here still does not have a complete explanation. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. October 19th, 2017. Halakala Observatory, on the summit of a volcano in Maui, Hawaii. A telescope called Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, was doing what it did every night, scanning the sky for anything that moved. Near-Earth asteroids, comets, objects that might one day pose a risk to our planet. Astronomer Robert Warwick was reviewing that night's data when he noticed something that did not belong. The object's trajectory was hyperbolic. That is the key word. Orbital mechanics sorts every object in the solar system into one of a few categories based on how it moves. Circular or elliptical orbits mean the object is bound. It goes around and comes back, like a planet or a comet originating in our own solar system. A hyperbolic trajectory means the object is moving too fast to be captured by the Sun's gravity. It is passing through. It comes from somewhere else. It will not return. No naturally occurring solar system object had ever been confirmed to have a hyperbolic trajectory from outside the solar system. This was the first, and it had been here for 6 weeks already. The closest approach to the Sun, the moment when the object was nearest to Earth and most observable, had occurred on September 9th, 40 days before anyone noticed. By the time astronomers realized what they were looking at, it was already leaving. Already more than 200 million kilometers past its closest point, moving away from the Sun at a speed that made every additional day of observation a race against physics. Telescopes around the world scrambled to look at it. The Hubble Space Telescope was redirected. Observatories from Chile to the Canary Islands collected data around the clock. Scientists had a narrow window, weeks at best, before the object became too dim and too distant to observe at all. The Hawaiians who named it gave it a word from their language, Oumuamua, roughly translated, the first distant messenger, or the scout. The observations came in, and the picture that emerged was unlike anything in the catalog of known solar system objects. The brightness of Oumuamua was not constant. It varied dramatically over time, brightening and dimming as it rotated, in a pattern that indicated an object with a highly irregular shape. Not a sphere, not a roughly rounded body like most asteroids, something extreme in its proportions. The initial analysis suggested a cigar shape, an object perhaps 10 times longer than it was wide, half a kilometer long, roughly 50 meters across, tumbling through space end over end. Later analyses of the same data suggested a different possibility, not a cigar, but a pancake. A flat, thin disk, very wide relative to its thickness, more like a piece of material than a conventional rock. Either way, nothing in our solar system looks like that. The most elongated asteroids we have ever characterized have aspect ratios of perhaps 3 or 4 to 1. Oumuamua's estimated ratio was 6 to 1 at minimum, possibly as high as 10 to 1. Its color was dark red, similar to objects in the outer solar system that have been processed by billions of years of cosmic radiation, developing a reddish organic crust. This was not unusual for an old object. The surface chemistry, though impossible to analyze in detail from Earth, was consistent with something ancient and well-traveled. But it was small, moving fast, already leaving, and the observations, impressive as they were for the circumstances, amounted to measuring the behavior of an object too small to photograph in any detail from millions of kilometers away, with telescopes that had not been designed for exactly this situation. What data scientists had was partial, but it was enough to reveal something that had no good explanation. When astronomers tracked Oumuamua's trajectory precisely enough to measure its actual path against its predicted path, accounting for all the gravitational forces acting on it from the Sun and every planet, they found a discrepancy. Oumuamua was not where it should be. It was slightly further along its path than gravity alone predicted. It was accelerating, not decelerating, as an unpowered object moving away from the Sun should do. This kind of non-gravitational acceleration has been seen before. Comets frequently show it. When a comet passes close to the Sun, ice on its surface sublimes, turns directly to gas, and those jets of escaping material act like tiny thrusters, pushing the comet slightly off its purely gravitational path. The effect is real and well documented. It is called outgassing, and it leaves a visible signature. A cloud of material around the comet's nucleus, a tail of gas and dust pointing away from the Sun. Astronomers looked for that signature in Oumuamua, with every telescope available, at every wavelength that might reveal outgassing or cometary activity. They found nothing. No coma, no detectable cloud of gas, no measurable release of material at any wavelength. The acceleration was real. The mechanism responsible for it was invisible. This is the detail that changed the conversation from interesting to extraordinary. A comet that outgasses leaves evidence. Oumuamua accelerated and left no evidence of any force producing that acceleration. The two facts, acceleration real, propulsion invisible, had no clean conventional explanation, and they still do not. In October 2018, a year after Oumuamua's discovery, Harvard astronomer Avi Loeb and his postdoctoral researcher Shmuel Biley submitted a paper to the Astrophysical Journal Letters. The paper did not claim that Oumuamua was alien technology. It did not speculate. It did exactly what a scientific paper is supposed to do. It considered the data and evaluated which explanations were consistent with it. And one of the explanations it evaluated was this: that the anomalous acceleration could be explained if Oumuamua had a very large surface area relative to its mass, that the pressure of sunlight itself, the gentle push of photons from the Sun, was sufficient to accelerate it, the same way wind accelerates a sail. For that to work, Oumuamua would need to have a surface area far larger than its estimated mass would suggest for a conventional rocky object. It would need to be extremely thin relative to its surface area, like a sail or like a sheet of material. The paper noted that a natural object this thin would be structurally difficult to explain. But it also noted that such dimensions would be consistent with what an artificial light sail, a propulsion technology that uses radiation pressure, would look like from the outside. The authors were careful. The paper said this was a possibility to be considered, not a conclusion. It was peer-reviewed. It was published. The scientific community's response was largely critical. The paper generated enormous media attention and significant backlash from astronomers who considered the alien hypothesis premature and sensationalistic. Loeb, who has spent his career producing peer-reviewed work in mainstream astrophysics, maintained that the scientific response should be to evaluate all explanations, rather than dismiss some on the grounds of their implications. The criticism of Loeb's work has not been that his math was wrong. It has been that natural explanations should be exhausted before invoking artificial ones, which is a reasonable scientific principle, but it requires having natural explanations that actually work. The scientific community has proposed several natural explanations for Oumuamua's anomalous acceleration. None of them is problem-free. The hydrogen iceberg hypothesis, proposed in 2020, suggested that Oumuamua was composed largely of molecular hydrogen ice. Hydrogen ice would sublimate, converting directly to gas without leaving a visible coma, because hydrogen gas is essentially transparent to the wavelengths used to detect outgassing from comets. The invisible outgassing would provide the invisible thrust. The problem is that hydrogen ice is not stable enough to survive interstellar travel. The radiation environment of interstellar space would destroy a hydrogen iceberg before it could travel the distances required to arrive in our solar system from another star. In 2021, a study published in the Journal of Geophysical Research Planets proposed a different candidate: nitrogen ice. A thin slab of solid nitrogen, like a piece of Pluto's surface knocked loose by a long-ago impact, would have the right density and surface properties to explain the acceleration. Nitrogen sublimating from the surface under solar heating would not produce a visible coma. This explanation is more physically plausible than the hydrogen iceberg, but it requires a very specific chain of events: a precisely sized and shaped fragment of nitrogen ice surviving interstellar transit intact, arriving with the right trajectory, and it has not been definitively confirmed as consistent with all the observations. More recent work has proposed that Oumuamua might be an extremely low-density porous structure, a kind of cosmic dust aggregate, with a very high surface area relative to its mass. This, too, has specific challenges in explaining why it would maintain structural integrity while tumbling through space. Every natural explanation comes with conditions attached. None is clean. By late 2019, Oumuamua was gone, too dim and too distant for any existing telescope to observe. It is now billions of miles from Earth, moving outward into interstellar space, and will never return. We have no second chance to study it. We had a window of weeks with limited telescope coverage, limited spectral data, and no ability to resolve the object in any image taken of it. Every conclusion drawn about Oumuamua's shape, composition, and behavior comes from indirect data, from how its light varied, how its trajectory deviated from gravitational predictions, what was and was not detected in searches for outgassing. In any other context, this would be an unsatisfying data set. For what may be the most significant object ever to pass through the solar system, it is what we have. This is why Oumuamua is still debated. Not because the data is ambiguous in its details. The details are reasonably well established. The acceleration happened. The absence of visible outgassing is confirmed. The unusual shape is inferred from the light curves. These are not disputed. What is disputed is what those facts mean when they are combined. Whether the combination of an unusual shape, unexplained acceleration, and absence of visible propulsion is a collection of extraordinary coincidences, or evidence of something that does not fit the category of natural solar system object. The second interstellar object detected in 2019 was called Borisov. It behaved completely normally. It had a visible coma, showed expected outgassing, and was almost certainly a conventional comet from another star. Its normalcy makes Oumuamua's abnormality more pointed, not less. In 2021, Avi Loeb founded the Galileo Project at Harvard. Its explicit mission is to systematically search for evidence of extraterrestrial technology near Earth. Not through radio signals. That has been the domain of SETI for 60 years. But through direct physical evidence. Objects that enter the solar system and behave unusually. Unidentified aerial phenomena observed in Earth's atmosphere. Any physical artifact that might indicate the presence of technology that did not originate here. The project has received significant funding. It has assembled a team of serious scientists, and it is conducting exactly the kind of systematic, data-driven search that Loeb argues the scientific community should have been doing for decades, rather than dismissing the question on the grounds that it sounds uncomfortable. Loeb's critics argue that the Galileo Project is chasing an answer rather than following the evidence. His supporters argue that the systematic avoidance of the alien hypothesis as even a subject of rigorous inquiry is itself a form of bias. That a scientific community which refuses to seriously test a hypothesis is not behaving scientifically. This debate sits at an interesting intersection of epistemology and astronomy. It is not about whether aliens exist. It is about what constitutes appropriate scientific methodology when dealing with a phenomenon that, if one explanation proves correct, would be the most significant discovery in the history of human civilization. The answer to that question has not been settled. Here is what the story of Oumuamua tells us, regardless of what it actually was. Our solar system is not isolated. Objects from other star systems pass through it. This was theorized, but never confirmed until 2017. Now we know it happens. We know that material, whatever kind of material, crosses the vast distances between star systems and occasionally arrives in our neighborhood. The interstellar medium is not empty and inert. It contains things that travel. If Oumuamua was natural, a fragment of a distant planet, a comet from another solar system, then it tells us that the building blocks of planetary systems are shared between stars. Material ejected from one system can reach another, potentially carrying with it complex organic chemistry or the kind of molecular ingredients that precede life. If Oumuamua was artificial, if it was a piece of technology, a probe, a piece of debris from an advanced civilization, then we had a close encounter with evidence of extraterrestrial intelligence, and we were not ready for it. We had no mission capable of reaching it, no probe that could intercept it, no instruments that could perform close analysis. We watched it through Earth-based telescopes from millions of kilometers away, and it left before we understood what we were looking at. Project Lyra, a concept study by researchers at the Initiative for Interstellar Studies, assessed whether a mission could be launched to chase Oumuamua. The answer was technically yes, but it would require extraordinary measures and years of travel time, and the object would already be billions of miles away and receding faster than any current spacecraft could chase. We were unprepared, and by the time we understood what had arrived, it was already gone. The broader lesson of Oumuamua is one that the scientific community has been slowly absorbing since 2017. We live in an era of discovery. Our telescopes are good enough, our survey programs comprehensive enough, that we are now detecting things that were theoretically possible, but practically invisible to previous generations of astronomers. Interstellar objects will pass through the solar system again. Astronomers now know to look for them and know what signature to search for. The Vera Rubin Observatory, when it begins full operations, will survey the sky with such frequency and depth that it is expected to detect multiple interstellar objects every year, giving scientists not a single frantic window of weeks, but repeated opportunities to study objects from beyond our solar system, with planned observations and dedicated follow-up. The next one may behave like Borisov, boring, normal, a comet from another star that does everything comets do. What is clear is that 2017 was not an anomaly. It was a beginning, a confirmation that the solar system is not sealed off from the rest of the galaxy, that the space between stars is not a barrier, but a highway, and things travel on it, and sometimes they pass through here. What those things are, whether all of them are rocks and ice, or whether one of them might be something else, is a question we are now positioned, for the first time in history, to actually try to answer. In September of 2017, something from outside the solar system passed through it. We did not know it was there until it was leaving. We scrambled to observe it. We collected data, and then it was gone, moving at 70,000 miles per hour into interstellar space on a trajectory that will never bring it back. What we have is a partial dataset, an unexplained acceleration, a shape unlike anything catalogued in our solar system, and a natural explanation that has not fully closed the case. Avi Loeb believes we should take the artificial hypothesis seriously until it is conclusively ruled out. Most of his colleagues believe it has not earned serious consideration yet. The data does not resolve the disagreement. It is the source of it. What is not disputed is this: Oumuamua was the first confirmed visitor from another star system. It behaved in ways we did not expect, and we were fundamentally unprepared to study it adequately. We did not have a probe ready to intercept it. We did not have instruments designed to analyze it up close. We did not even know it existed until 40 days after it made its closest pass. Whatever it was, and the honest answer is that we do not know, it exposed a gap in our readiness for exactly the kind of encounter that our models of the universe suggest should happen. Oumuamua came and went. The next one will come. And the question worth asking now, while we have time to prepare, is whether we will be ready to actually find out what it is. What do you think Oumuamua was? Leave your answer in the comments, and subscribe, because when the next one arrives, we will be covering every detail as it happens.